Hello. We'll be learning about relations and functions, which is the first chapter in class 12 NCERT. Okay, so in today's session, we will be learning about what are relations and what are its types. Okay, so before starting the actual topic or before diving into the topic, we should know some basics. So we'll have a quick recap of what we have learned in class 11, like the only topics which are required to understand the class 12 topics. Okay, so our chapter is so our chapter is relations and functions, correct? So we'll start with sets. Okay, so what are sets? Okay, we know that sets are collection of well defined objects, okay, that are universally accepted. Okay, so what do we mean by universally accepted? Okay, universally accepted means this set. Okay, if we are giving an example of a set, then it should not vary from person to person. Like, for example, if I ask, suppose there are two people, okay, one is Rahul, second is Sonia. Okay, if I ask Rahul, tell me the favorite three favorite sports. So he might tell basketball, cricket, and football. But if I ask the same question to Sonia, the set may be different because for her, the favorite sports might be different. It may be swimming, chess, volleyball, something like that. So, universally accepted means it should not vary from person to person. Okay. So for example, uh, so we'll give an example. Okay, a set of vowels. Set of vowels. Okay, okay. Let us denote this set with capital letter A. Generally, these sets are denoted with capital letters only. Okay, so what is A actually? A is the set of vowels, and when we have to write this set, we generally like we make curly brackets and write whatever elements are there in the set. Okay. So in case of set of vowels, we know we have A, E, I, O, and U. Okay. This particular form of representation is called a roster form, in which we make curly bracket and write whatever elements are there. We write the elements as it is. So this is called roster form. We have learned one more form in class 11, which is the set builder form. Okay. In this case also we make curly brackets and we say this set A is the set of all x such that, okay, this line say meaning of this line is such that, okay, the set of all x such that X is a vowel in English alphabet. Okay, so this particular representation is called the set builder form. Okay, now let's take one more example. Let it be example number one. We'll see another example, which is example number two. Okay, let it be set of primes less than 10. Okay, so let us represent this set as B. Okay, so if we have to represent this particular set in roster form, what we can do is we can write the entire set. We can write the elements, entire elements of the set as it is. So the first prime number is 2, then we have 3, then we have 7. Okay, there is one more element which is 5. Okay, so these are the four prime numbers less than 10. Note that 1 is not a prime number. Okay, so this particular representation is the roster form. Okay, and then again we have a set, another representation which is the set builder form, wherein we write x is the set of like this, b is the set of all x such that x has exactly two divisors, one and x itself. Okay, this is definition of prime. Okay, but then we have one more condition that it is less than 10. So we write a comma and x is less than 10. So this particular uh, okay, so this is how we represent this particular set B as set builder form. Okay, so now we should know what is cardinality of a set. Okay, so cardinality of a set is nothing but the total number of elements in the set. Okay, so for example, we have seen in our first examples that is the set of vowels. Okay, the set of vowels. Okay, we'll consider the same notation again. So the set of vowels we have represented it with the letter A. So it is A, E, I, O, and U. Okay, cardinality of a set means number of elements in the set. Okay, so how many number of elements are there in set A? We have A, E, I, O, and U. So these are five elements. Okay, so the cardinality of set A, okay, is 5. Now cardinality is represented as n of A or by this symbol. Okay, this is the representation. Okay, representation. Now n of A is equal to 5 that we have seen. Similarly, in example 2, we had seen B, the set of primes less than 10 is equal to this particular set, which is B is equal to 2, 3, 5, and 7. Now, how many elements are there in set B? Set B, we have 4 elements, correct? So, the cardinality of set B is 4. Now, the question arises, what happens? Like, is it possible that there are no elements in set, in a particular set? Okay, so suppose there is a set C such that cardinality of C is 0. Okay, this means there are no elements in set C. Okay, and such a set is called C is a null set, or we say C is an empty set. Okay, It is generally denoted as C is equal to 5. 5 is empty set, okay? It is a representation. Or we can also write C curly brackets in which no element is there. So we say that there is no element in C. Okay. Now, in this chapter, we'll be using a lot of symbols also. So we need to know all those symbols. Okay. So symbols used in set. Okay. The first symbol looks like an E, but it is not E. Okay. It means belongs to. Okay. So suppose we have we if it is written 2 belongs to A, so it is read as the the element 2 belongs to the set A. Okay, the element 2 belongs to the set A. Okay, it basically means that 2 is an element which is contained in or which belongs to the set A. Okay, 2 is an A. Now, the second symbol that we have is this this symbol. This represents there exists. So, for example, if we write there exists 2 belongs to Z. Okay, Z in general is the set of integers. Okay, so this particular thing means there exists this symbol. There exists an element 2 belongs to set of integers. Okay, now how many over? 2 over. Third symbol is this E with a cross. Okay, this is does not belong to, not belongs. Okay, so if we write 2 does not belongs to A, so it is read as 2 does not belongs to A. This means 2 is not in the set A. Okay, then the fourth one is the upside down A. Okay, it looks like upside down A. It means for all. The fifth is these two dots or this line. This means such that. We have seen this in the set builder representation, right? So now the sixth one is this is it means subset. Okay. So for example, A is a subset of B. So we have two sets A and B, and A is a subset of B, which means this set A is contained in set B. Okay. Every element of set A is an element of set B. This is its meaning. Okay, we'll look deeper into this subsets and all later. Now, next symbol is this U, which represents union. After that, we have this upside down U, which means intersection. Then lastly, we have this 5, which I've already told you, null set. Correct? Now, let us move to the next topic, which is the Cartesian product. Okay, so suppose we have two sets. Okay, two sets A and B. Then Cartesian product is def uh, before defining, we'll see how it is denoted. Okay, so it is denoted by A cross B. Okay, so I'll tell you what is the meaning. Suppose we have a set A. Okay, sorry. Okay, so okay, this is set A and this is set B. So suppose we have four elements in set A, which is A1, A2, A3, and A4. And there are two elements in set B, which is B1 and B2. So the Cartesian product is, okay, I'll write the definition first. Okay, Cartesian product is the set of all ordered pairs A comma B such that A belongs to A and B belongs to B. Okay, so in this case, how can we write A cross B? Okay, so what we'll do? A will write A1 with B1. Okay, A1 B1 bracket. Then second element A1 B2 A1 B2. Third element uh, A2 B1 A2 B1. Fourth element A2 B2 A2 B2. Fifth element A3 B1 A3 B1. Sixth element A3 B2 A3 B2. Similarly, seventh element A4 B1 and last element A4 B2. Okay, this is the Cartesian product. Cartesian product. Similarly, we can find what is B cross A. Okay, okay. So now we have here same sets, but we need to find what is B cross A. So we'll write B first. So the elements were B1, B2, and here we had A1, A2, A3, and A4. So what is B cross A? B cross A will be B1 in B1 A1, B1 A1, B1 A2, B1 A2, B1 A3, B1 A3, B1 A4, B1 A4. Similarly, now we'll have B2 A1, B2 A1, then B2 A2, B2 A3, then B2 A4. Okay. Now if you see A cross B and B cross A both are Cartesian products. Number of elements in both the Cartesian products is same, which is 8. but both are not equal. That is, the elements in both the sets is not at all equal. Okay, so A cross B is not equal to B cross A in general, but there may be cases where A cross B will be equal to B cross A. Okay, now we'll move on to our next topic, which is relations. Okay, so formally, relations, if we look at the formal definition, relation from set A to B are subsets of Cartesian product, okay, of A cross B. Like we are saying from set A to set B, so we are writing A cross B. If we had said from set B to set A, then we would have written B cross A. Okay. Now, if we have two sets, okay, and okay, if we have two sets A and B, and the cardinality of A is equal to M, the cardinality of B is equal to N, then the cardinality of A cross B, which is the Cartesian product, um, then cardinality of A cross B is equal to M dot N, okay, which is the cardinality of A into cardinality of B. Also, number of possible relations is equal to 2 to the power M dot N, okay, which is equal to 2 to the power cardinality of A cross B, or 2 to the power cardinality of A into cardinality of B. Okay, this particular formula or this particular relation is very important. Okay. It is very, very much important. How did we find this formula or this relation is not important right now. It can be easily found out with the permutation and combination, with the concept of permutation and combination, which we have already learned in class 11. But as we are in class 12, we don't need to find how these values came, okay, how this relationship came. But we need to memorize this particular expression, okay. So, for example, okay, based on this particular relation, uh, I'll give you an example. So, example, okay, we have two sets, again A and B. Now, this is set A, this is set B. Okay, the elements of set A are 1, 2, 3, and the elements of set B are A and B. Here I'm writing it in form of pictures or pictorial representation, but the formal representation is the roster form and the set builders form. Okay, so we should write in exam, we should write the definitions and problems with that particular representations only. Okay. Now, what do we have? Like, if we find the Cartesian product A cross B, it will be 1 to 1A, 1A, then 1B, 2A, 2B, 3A, 3B. Correct? So now total number of possible relations will be equal to 2 to the power. How many elements are there in A cross B? We have 1, 2, 3, 4, 5, and 6. Then the total number of possible relation will be 2 to the power 6, and this will be 64. So there are 64 relations that are possible with these very two small sets. Okay. So we'll write some of the relations, which is first is R1 is equal to 5. So 5 means none of the elements of A is connected to elements of B. So there is no relation at all. So this is also one relation that nothing is mapped. Okay. No element of set A is mapped with any other element of set B. So this is first relation. Then R2 we can write it as 1 comma A. Okay. You can take one element and write R2. R3 we can write as 1 comma B. R4 we can write as 2 comma A. Similarly, something will get, then we'll get R, it will be RA. Okay. Then we can write, okay, R2 to R7 will be singlets. Like only one element will be there in those relations. Now R8 will be doublets. Like there will be two elements, 1 comma A and 1 comma B can be there. Then R9 can be 1 comma A, comma 2 comma A. These two can be there. Like this, we can have different combinations of two elements. Okay, then we can make subsets which will be relations. So there will be some uh, doublets also. Then we will have triplets, like three elements from A cross B we can take and we can form a relation. So there are there are many combinations possible. Then we can take four at a time, then we can take five at a time, and lastly we can take six at a time. Six at a time means we take every element because there are only six elements in A cross B. So last relation, which is R64, last relation will be A cross B only. Okay, like this 64 relations are possible. Now we'll talk about relation in A. So relation in A means what? Relation in A means we have one set A, okay, and we have another set A, okay. This means we have only one set, that is A. And relations in A are nothing but subsets of A cross A. Earlier we had relations as if when we had two relations where we had to define a relation from A to B, we had to consider the Cartesian product A cross B. Now we have relations in A, that is from A to A. Okay, this is A and this is again A. So we need to find relations between A and A. So we need to find subsets of A cross A. Okay. So now for example, if we have to talk about the cardinality, now we have this set A. and here also we have set A. Suppose we have n elements here, 1, 2, till n. Similarly, if this is A, this is also A, then the number of elements will be common, will be same, and the elements will be common. So it will also be 1, 2, and so on till n. So cardinality of A is equal to n. Cardinality of A is equal to n. Okay. Now cardinality of A cross A will be equal to cardinality of A into cardinality of A, which we have already seen now, and this is equal to n into n, which is n square. Okay. Now the possible number of relations will be 2 to the power cardinality of A cross A, which is nothing but n square. So it will be 2 to the power n square. Correct. Now we are done with the basics. Now we'll move to the actual topic. Okay. So now we have types of relations. So, and if we see, there are many types of relations. For example, we have empty relation, universal relation, identity relation, reflexive, irreflexive, symmetric, asymmetric, antisymmetric, transitive, and many more relations are there. But in our class 12th syllabus, we don't have those many relations. We have limited number of relations. So first we'll discuss about empty. Uh, we'll first discuss about empty relations. Then we'll discuss about universal relations. After that, we'll discuss about identity relation. Okay. So what is empty relation? One second. So formally, an empty relation. Okay, a relation in R is called empty if no element of A is related to any element of A. Okay, so I'll write the definition also. Uh, relation R is called an empty relation if no elements of A is related to any element of A. So what does this mean? Okay. So again, we'll con we'll consider the set A. Okay. So we have suppose some elements. Suppose element 1, 2, 3. Here also we have 1, 2, 3. As both the sets are same, both the sets are A only. So the elements will be common. Now we have a relation R in which we do not have any element. Okay, that means none of the elements of A. which is from this set, is mapped with any other element of this set, any element of this set. So no mapping is possible. This is not possible. This is not there. This is not there. Like this, no mapping is there. So R is an empty relation. Or similarly, or we can write it as R is equal to null set. Okay, so this is called empty relation. Okay. Now we have, okay, I'll give you an example for this. Okay, suppose we have a relation R, which is a set of all A comma B such that A dot B is equal to 50. Okay, and A and B belongs to A. Okay, so what are the elements in this relation? We are considering the same set. Okay, so it is given that this relation contains only those elements A comma B for which A into B is 50. If we take the highest possible value for this set A, which is 3, so 3 if multiplied with 3 will be equal to 9. Okay, which is 3 into 3 is equal to 9, which is not equal to 50. There is no two elements in set A which on multiplication will give 50. So we have R is equal to empty relation. Okay. Now we'll talk about universal relation. Okay. Okay. Now formal definition for universal relation is a relation in R is called universal relation if each element of A is related to every element of it. Okay, I'll write it for you. A relation in R is said to be universal relation if each element of A is related to every element of A. Again, let us consider the same set, which is A and A, and it consists of 1, 2, 3. Here also we have 1, 2, 3. So now uh, every element of A is connected or mapped with every element of A. So 1 is mapped with 1, 2, and 3. Similarly, 2 is also mapped with 1, 2, and 3. And also 3 is mapped with 1, 2, and 3. So here we can see that every element of A is related to every other element of A. So this is called a universal relation. So R in this case is A cross A. Okay. In the case of empty relation, we had R is equal to 5. And in case of universal relation, we have R is equal to A cross A. Now, for example, I'll give you an example. Suppose this particular set or this particular set A only will consider. So R is defined as the set of all A comma B such that A minus B is an integer. Okay, so we can see also we have A and B belongs to A. So we can see in the set A every number is an integer. 1 is an integer, 2 is an integer, 3 is an integer. So if every number is an integer, then a difference of these integers will again be an integer. So if we subtract uh, 1 with 1, it is 0. It is 0 is an integer. 1 minus 2 is minus 1. It is an integer. 1 minus 3 is minus 2. This is an integer. 2 minus 1 is an integer. 2 minus 2 is an integer. 2 minus 3 is an integer. 3 minus 1 is an integer. 3 minus 2 is an integer. 3 minus 3 is an integer. So we have R is the whole Cartesian product. That is R is equal to A cross A. Now let's move on to identity relation. Okay, so identity relation R is defined as the set of all A comma A such that A belongs to such that A belongs to the capital set A. Now we will consider similar example, similar set, which is our set A, and it is consisting of the elements 1, 2, 3, and 4 also. Here also we have 1, 2, 3, and 4 because the sets are same. Now, R is defined if R is defined such that one is related to 1 only, 2 is related to 2 only, 3 is related to 3 only, and 4 is related to 4 only. This which means R is equal to, in this particular case, 1 comma 1, 2 comma 2, 3 comma 3, and 4 comma 4. Okay, this particular uh, example is an example of identity relation. Okay, but if we have an element 1 comma 2 also in this, suppose R is equal to 1 1, 2 2, 3 3, 4 4. We have like this, and we have 1 comma 2 also, then this is not an identity relation. In case of identity relation, keep it in mind that if we have any other element except A comma A, then it is not an identity relation. Now we'll move on to reflexive, symmetric, and transitive relations, which are very much important for the exam. So, reflexive, symmetric and transitive relations. Okay, so first is reflexive relations. Now, a reflexive relation is a non-empty relation. Okay, a non-empty relation, or will write a relation is said to be reflexive if A comma A belongs to R, which is belongs to the relation. For every, it is for every A belongs to A. Okay, it is not for like some A, it is for all the A's. Okay, now for example, we have here the elements 1, 1, 2, 3, 1, 2, 3. This is set A. This is set A. So we are defining relation 1. Okay. This is 1 maps to 1, 2 maps to 2, 3 maps to 3. Now we can see A comma A is belonging to R. Okay. Now this will be written as R1 is equal to 1 comma 1, 2 comma 2, 3 comma 3. Okay. For every A belonging to A, we have made a relation A comma A. So this is a reflexive relation, and it is also an identity relation. Okay, we have seen earlier that this is an identity relation. So this is an identity relation, reflexive relation, and identity relation as well. Okay, now we'll consider um, one more relation. This is relation 2. Again, we have the same element, same set, 1, 2, 3, 1, 2, 3, A, A. Now, here, if 1 is mapped to 1, 2 is mapped to 2, okay, then we have R2 is equal to 1 is mapped to 1, 2 is mapped to 2, that's it. So, this is not a reflexive relation, as by the definition we should have a comma A for every A belongs to A. One second. Okay. Okay, we'll just continue as it is already recorded. We'll just continue. Okay. Okay. So we were talking about R2. Okay. So we have elements one, 2, 3, 1, 2, 3. So R2, in R2 we had 1 to 1 is mapped to 1, 2 is mapped to 2. So R2 is basically 1 comma 1, 2 comma 2. And this is not a reflexive relation, as 3 comma 3 does not 3 comma 3 does not belongs to uh, the relation R2, because by definition of reflexive relation, we should get A comma A belongs to R for every A belongs to A. But here we do not have 3 comma 3 for 3 belongs to A. So this is not a reflexive relation. Now, okay, okay, this much is enough for reflexive relation. Okay, one more example we'll see for reflexive relation. So here we have again the same elements 1, 2, 3, 1, 2, 3, A, A. Now here we have 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 3, 1 is mapped to 2, and 2 is mapped to 1, suppose. So we have the relation 3 as 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 3, and we have 1 is mapped to 2, and 2 is mapped to 1. Now this is also a reflexive relation. Okay, reflexive relation. Okay, as we have 1 comma 1, 2 comma 2, 3 comma 3. Okay, for 1 we have 1 comma 1, for 2 we have 2 comma 2, for 3 we have 3 comma 3. Rest any element if we have, that doesn't matter. Okay, we it is or it and it will be a reflexive relation if 1 comma 1 is there, 2 comma 2 is there, 3 comma 3 is there. For example, if we add another element 4, if 4 comma 4 is also there, which is if 4 comma 4 is also there, then this is a reflexive relation. Okay, now we'll move to a topic where students might have confusion. Okay, reflexive relation and identity relation. Okay, suppose I'll consider I'll consider some other example. Okay, this is set B. This is also set B. Okay, it consists of elements A, B, C. This also consists of elements A, B, and C because all both the sets are same. Okay, now reflexive relation. Okay, I'll write an example. It will be clear for you. Okay, reflexive identity. The example of reflexive relation is A, comma A, B, comma B, C, comma C. This is one of the examples. Another example can be A, comma A, B, comma B, C, comma C, A, comma C, like this. But we can have several examples of reflexive relation. How many that we don't have to worry about because again, that we can easily find out with the help of permutations and combinations. But now we can write several examples, many more examples of reflexive relations. But we can only write one identity relation. Okay, that is A comma A, B comma B, C comma C. That's it. If any other element is added here, then it won't be an identity relation. So it is, so reflexive relations are not unique, but identity relations are unique. Okay. Also, a reflexive relation may or may not be identity relation, but identity relation is always reflexive. Okay, now we'll move on to symmetric relation. So, for example, okay, simple meaning, I'll write the formal definition first, then I'll explain it to you also. If A comma B belongs to R, then this implies that B comma A is also in R. Okay, meaning if we have two sets, or not two sets, if we have only one set, uh, which is this set A, this is also set A. Here we have one, two, three. Here we have one, two, three. For example, if we have R in which a relation R in which one is mapped to two, then for this relation to be symmetric, we should also have two mapped to one. So R is equal to 1 comma 2, 2 comma 1. This is symmetric relation. Some more examples. Okay. If R1 is equal to 1 comma 2, 2 comma 3, 3 comma 2, then this is not symmetric. Why? The reason is because for 1 comma 2 belonging to R1, we do not have 2 comma 1 belonging to R1. Okay. If 2 comma 1 would have been there in this relation R1, then it would have been symmetric. Okay. Now our hypothesis is if A comma B belongs to R. Suppose suppose there is no A comma B belongs to R. Okay, which means if R is empty, okay, then there is no A comma B. Then there is no A comma B. If A comma B is not there, then we cannot talk about B comma A. Okay, so if R is empty, it is automatically symmetric. Okay, this you should remember. You might face some difficulty to accept the fact that if it is empty, then it is symmetric. But you should, if you are not able to understand it now, you will be able to understand it eventually. So till then, if you're not able to understand, just keep this in mind. If it is empty, it is symmetric. Okay. Now we'll move on to transitive relation. Okay. Here, if we have A comma B, if we have A comma B belongs to a relation R and we have B comma C belongs to R, then it will imply that A comma C belongs to R. If this happens, then the relation is transitive. Okay. So for example, we have a set A, a relationship defined from set A to itself, which is set A to A, which is also called a relation in A. So I'm taking the same set again and again for you to understand. Okay. So this is one, 2, 3, 1, 2, 3. Okay. Now what we have is suppose 1 is related to 2 and 2 is related to 3. This is R. R is equals to 1 is related to 2, 2 is related to 3. Now we know that 1 is related to 2, 2 is related to 3, then 1 should relate to 3. That is, 1 should be related to 3 as well. Okay. Then this relation is transitive. This is an example, okay, for understanding purpose. Now, here in this example only, if we have a set R1 which is equals to 1 comma 2, 2 comma 2, okay, is this relation transitive? Okay, so we see 1 is mapped to 2 and 2 is mapped to 2, so we should have 1 mapped to 2. Yani, that means this should exist and this is already there. So this is also transitive. Okay. Now another example 1 comma 2. Okay. Now we have here 1 comma 2. Okay. I'll come to this point little afterwards. So I'll give you one more example. R2 is equal to 1 comma 2. We have 2 comma 3. So, so is this transitive? So we have 1 is related to 2, 2 is related to 3. So 1 should relate to 3, which is the same thing which we have taken here. So but 1 comma 3 is not in R2, then this gives R2 is is not transitive. Correct. Now, now we have the hypothesis that A comma B belongs to R and B comma C belongs to the same relation. Then if A comma C belongs to R, it is said to be transitive. But what if this exists and this does not exist? If A comma B belongs to R and B comma C is not there in R, then we cannot talk about A comma C. So if we cannot talk about A comma C, we say that automatically the relation is transitive. This again is something difficult to digest, but eventually you will understand what is it if you're not able to understand it now. So for example, I'll give R3, okay, which is equal to 1 comma 2. Okay, so we have 1 comma 2 here, but we don't have any other element such that 2 is mapped to some element. Okay, we do not have 2 uh, comma x. Okay, 2 comma x for some 1 second here here we do not have 2 comma x 2 comma x belonging to R3 for some x belonging to A. So we cannot talk about 1 comma x. Okay, therefore R3 is transitive. Okay, we have 1 comma 2, but we do not have any element such that 2 comma something is there. So we do not have such an element. So we cannot talk about the last element, that is A comma C. We cannot talk about this element. So if we cannot talk about this element, then we say that it is transitive. Similarly, if we have R4 is equal to 5, which is an empty set, okay, then we do not have this first only. If we do not have the first element, we cannot talk about the second element, and eventually we cannot talk about the third element also. So this is automatically, I'll write here also automatically for you to remember what it is. It is not automatically, there is logic here, but I'm writing it for your purpose so that it will be easier for you to remember. So R4 is equal to 5 is also transitive automatically. Okay. Now we have seen what is reflexive relation, what is symmetric relation, what is transitive relation. Okay. We have seen plenty examples also. So what are equivalence relation? This is the last topic for this session. Okay. So a relation which is reflexive, transitive, and symmetric, all three, then it is said to be an equivalence relation. Relation which is um, reflexive, symmetric, and transitive is called equivalence. Okay, so this is our topic. We'll do few basic questions on this, 2 or 3 questions, and then we'll end the session. So, question number one. Suppose we have a set A which is 1 comma 2 comma 3, which is the same set, okay, and we have defined a relation R, okay, which is 1 comma 1, 2 comma 2, 3 comma 3, 1 comma 2, 2 comma 3. So we have to find we have to tell whether it is reflexive or not, symmetric or not, or transitive or not. So solution, checking for reflexive. Okay, first we will check for reflexive. We can see 1, 2, 3. So 1, 1 should exist, 2, 2 should exist, 3, 3 should exist. So 1, 1 is there, 2, 2 is there, 3, 3 should there. So we say that uh, there exists A comma A belongs to R for every A belonging to capital A. Therefore, R is reflexive. Okay. Check for symmetric. So for symmetric, we know if A comma B belongs to R, then B comma A should belong to R. Okay, so we have 1 comma 1. 1 comma 1 is there. Then if we interchange it, then also it is 1 comma 1. It exists. Similarly, 2 comma 2, 3 comma 3. Okay. If 1 comma 2 is there, then 2 comma 1 should be there. But it is not there in R. Therefore, R is not symmetric. Similarly, 2 comma 3 is there, but 3 comma 2 is not there. Therefore, it is not symmetric. Okay. So, to disprove something, to disprove that it is not symmetric, we just need to show counter example. So, we can just write for 1 comma 2 belongs to R, we do not have 2 comma 1 belonging to R. Therefore, it is not symmetric. Okay. We know we have one more counter example which is 2 3. I'll tell you another way to write it. For 2 comma 3 belongs to R, 3 comma 2 does not belongs to R. Therefore, R is not symmetric. Okay, then check for transitive. So we have 1 comma 1. Okay, 1 second. Erase it to make it clear. Okay, now see, we have 1 comma 1 and we have here 1 comma 2. So 1 comma 1 is there, 1 comma 2 is there. So this 1 comma 2 should be there, which is here. Then we have 2 comma 2. We have 2 comma 3. Okay. Then 2 comma 3 should be there. It is there. Again 3 comma 3 is there. But okay, we cannot talk about second. Okay. Now we see 1 comma 2 is there, 2 comma 3 is there. So 1 comma 3 should also be there. But 1 comma 3 is not in relation. So we write a counter example that 1, what is that? 1 comma 2 is there. 1 comma 2 belongs to R and 2 comma 3 belongs to R, but 1 comma 3 does not belongs to R. Therefore, R is not transitive. Okay. Okay. We'll do one last problem, which is um, suppose uh, we have a set of triangles. Okay, and the relation is R is triangle 1 is congruent to triangle 2. Okay, then we have to check whether it is reflexive, symmetric, or transitive. Or okay, solution. We have uh, reflexive. So triangle T1 is always congruent to itself. Therefore, we can write T1 comma T1 belongs to R for every T1, okay, set of triangles which is it. Therefore, the relation is reflexive. Okay, check for symmetry. If T1 comma T2 belongs to R, that is T1 is congruent to T2, then we have T2 is congruent to uh, T1. Okay, we can write like this, better write this notation. So therefore, if T1 T2 belongs to R, this implies T2 T1 belongs to R. Therefore, symmetric. This relation is symmetric also. Talking about transitive, if T1 comma T2 belongs to the relation and T2 comma T1 belongs to this relation, then T1 comma this T3 should also belong to this relation, because if T1 is congruent to T2 and T2 is congruent to T3, then we know that T1 will be congruent to T3. So therefore, the relation is transitive. So this is all for today's session. I hope you understood. Keep studying. Be happy.